Gravity, one of the four fundamental forces of nature, plays a pivotal role in shaping the structure and functioning of the universe. Around planets, stars, and black holes, gravity not only keeps celestial bodies in orbit but also clearly defines the extent of their influence. The unique aspect is that this affected area typically takes on a spherical shape, as the force spreads uniformly in all directions. A black hole, one of the most mysterious entities in the universe, is often depicted as a perfect sphere capable of devouring everything around it. However, recent discoveries in theoretical physics have left scientists questioning, is the true shape of a black hole really as simple as we once thought? This question has sparked a vast journey of exploration, spanning from classical physics to advanced theories of extended dimensions, promising to completely transform our understanding of the universe. So why are black holes believed to be spherical? In the universe that humans have explored, gravity is the key factor determining the shape of all celestial bodies. When massive stars exhaust their fuel and collapse, they form black holes. In this process, gravity pulls all matter toward the center, giving black holes an almost spherical shape. This also holds true for the event horizon, the boundary surrounding a black hole, where nothing, not even light, can escape. In a universe with three spatial dimensions, left, right, up, down, front, back, along with one dimension of time. Classical physics calculations all prove that black holes are spherical in shape. This formation process is similar to how planets and stars are formed. As the cloud of gas and dust accumulates, under the force of gravity, it compresses into a sphere. Therefore, the concept of a spherical black hole has been widely accepted by astrophysicists. In recent years, theoretical physics has opened the door to possibilities far beyond conventional concepts. String theory, one of the most prominent theories, posits that beyond the three familiar spatial dimensions humans can perceive, the universe may contain additional dimensions. These empty spaces, though invisible to the naked eye, are untouchable by hand. It can profoundly influence how objects move through space. In this situation, the black hole's spherical rule may no longer be accurate. Modern mathematical studies have conducted surveys to determine the possible geometric forms that black holes can take in higher dimensional spaces. The results are astonishing. Black holes can exist in completely different forms, such as torus-shaped or other complex structures. This raises an important question: do those strange shapes exist only in theory, or do they truly exist in the universe? The idea of non-spherical black holes could change how we conceive of the universe. Although there is no direct experimental evidence to prove it, these hypotheses have opened up countless promising new possibilities. It's like suddenly seeing a door we never imagined, opening up a universe filled with wonders far beyond our imagination. These strangely shaped black holes could help us gain deeper insight into the nature of gravity in higher dimensional spaces. This holds immense significance in unifying Brother Seng's theory of general relativity with quantum mechanics. The two pillars of modern physics still don't truly harmonize with each other. Particle physicists not only study theory but also actively seek experimental evidence to verify the existence of additional spatial dimensions. One of the research methods involves using large-scale particle accelerators, such as the Large Hadron Collider, LHC, to simulate high-energy collisions, which could potentially produce extremely small black holes. If we could observe these black holes, even if they exist only for a fleeting moment, they could confirm the existence of extra dimensions and bring the theory of non-spherical black holes closer to reality. In the past 20 years, numerous studies have proven that black holes existing in higher dimensional spaces can possess diverse and complex shapes. According to calculations, black holes not only exist in spherical form but may also possess previously unknown, bizarre geometric structures. The interplay between theoretical and experimental physics, along with the profound connection between mathematics and astronomy, is bringing humanity closer to unraveling the universe's greatest mysteries. Does this universe still hold mysteries beyond our sight? What laws govern the cosmos that humanity has yet to fully comprehend? Mathematics is the language of the universe. Through it, we can accurately describe and predict all physical phenomena. By observing celestial objects, astronomy provides data and real-world context to verify mathematical and physical theories. Theoretical physics and experimental physics do not exist in isolation but always support and drive each other's development. Theoretical physics constructs models and hypotheses based on mathematical foundations and logic, while experimental physics tests those hypotheses through observation and experimentation. When there is a discrepancy between theory and experiment, scientists will review the theory, make adjustments, or in some cases, construct an entirely new theory. For a long time, the scientific community widely held the view that black holes were always spherical in shape. However, advances in theoretical physics and research on higher dimensions have cast doubt on this perspective. Why do celestial bodies in the universe have a spherical shape? When gazing at the sky through a telescope, whether from Earth or outer space, you'll discover something truly fascinating. Most objects in the universe are spherical in shape. Whether it's a distant star from Earth or a strangely shaped planet, being spherical seems to be the general rule. The cause of this phenomenon is gravity. When a planet or star reaches a sufficiently large mass, its gravitational force pulls surrounding matter toward the center, giving them a spherical shape. After the Big Bang 13.8 billion years ago, tiny dust particles in massive gas clouds gradually collided and merged together. One collision followed another, gradually forming smaller and smaller spheres. When the mass of a celestial body increases, its gravitational force also becomes stronger, drawing in more matter from the surrounding environment. This process leads to the formation of stars and planets. All matter tends to move toward the center of gravitational force, and the sphere is the only shape in space that allows every point on its surface to balance this force perfectly. However, not all planets are perfectly spherical. Although gravity favors a spherical shape, in reality, many planets are not completely round. For example, gas giants like Jupiter and Saturn have bulging equators due to their rapid rotation. According to NASA, Saturn looks like a squashed basketball. Even our own Earth isn't a perfect sphere. The main cause is the centrifugal force from rotational motion, which causes it to bulge slightly at both poles, forming what is known as an oblate spheroid shape. On the other hand, smaller celestial bodies like asteroids or comets often have irregular shapes, ranging from misshapen to potato-like, because their mass is too small for gravity to compress them into a spherical form. For example, Mars' moon Phobos has a peculiar shape, resembling a giant potato. Out of the more than 300 moons discovered in the solar system, only about 20 satellites have a perfectly round shape like the image we often imagine. Gravity not only creates balance in the universe but also determines the shape of most celestial bodies. However, the universe still holds countless fascinating exceptions, from asteroids with bizarre shapes to giant gas planets with their signature bulging bellies. Those imperfections do not diminish the beauty, but rather, they further highlight the wonder and complexity of the universe we are gradually uncovering.